Hello everyone, and welcome to the Waveshare ESP32 Arduino Getting Started tutorial. In this lesson, we will learn about a very popular serial communication protocol, I2C. You will see it on many peripherals, such as sensors, real-time clocks, and the OLED display we will use later. Let's get started. The I2C bus, short for Inter-Integrated Circuit, is a widely used two-wire serial bus. First, let's look at the wiring. On an I2C bus, there are two core signal lines. SCL, the serial clock line. The master generates a clock signal to synchronize the timing of all data transfers. SDA, the serial data line. It is responsible for bidirectional transmission of actual data. Additionally, all devices must connect to ground to achieve a common reference voltage level. On an I2C bus, devices are divided into two roles. Master device, usually a microcontroller, such as the ESP32. Slave device, usually peripherals such as sensors, memory, etc. An I2C bus can support one master with multiple slaves, or even multi-master, multi-slave modes. One additional note, the I2C specification has updated the master-slave terminology to controller target. However, because the master-slave terms are still commonly used in the ESP32 ecosystem, this tutorial will continue using the older terminology for ease of learning. The master device communicates with a specified slave device using the device's address. I2C typically uses a 7-bit address, set by the manufacturer during chip production. For example, the OLED in our example uses 0x3D. When the master initiates communication, it first broadcasts an address. Only the slave device with a matching address on the bus will respond. Finally, let's look at these two pull-up resistors. They are critical for the I2C bus to function correctly. Simply put, devices on the I2C bus can only pull the signal line low, but cannot actively drive it high. This design is called an open drain structure. When the bus is idle, these two pull-up resistors are responsible for pulling the signal line back to a high level. ESP32 series chips typically have one or two built-in I2C controllers. In the Arduino environment, the ESP32 I2C library is based on the Arduino wire library and adds a few more APIs. You can use I2C functions with the following objects. The wire object corresponds to the first I2C controller by default. The wire1 object corresponds to the second I2C controller and can be used simultaneously with wire to achieve two independent I2C buses. Unlike the fixed I2C pins on traditional boards like the Arduino Uno, the I2C pins on the ESP32 can be flexibly configured. Its I2C functions can be routed to almost any GPIO pin through the GPIO matrix and pin multiplexer. We will explain how to set the pins in a later example. Okay, let's get hands-on. When you get a new I2C module, the first task is to determine its address. Although you can look it up in the datasheet, using a scanning program to directly find the address is more convenient and efficient. Components needed: one ESP32 development board, one breadboard, one I2C module, two 4.7 kiloohms resistors, a few jumper wires. Please connect the circuit according to the wiring diagram on the screen. Here we define SDA as GPIO1 and SCL as GPIO2 and connect them to the corresponding pins of the module. Also, pull up SDA and SCL to 3.3 volt with two 4.7 kiloohms resistors. Note: many I2C modules already have built-in pull-up resistors, so external ones are not needed. If unsure, please consult the module documentation or schematic. Additionally, the screen used in this example supports both SPI and I2C interfaces. You switch between them by reconfiguring the 0-ohm resistors at the BS1 and BS2 solder pads on the back of the module. By default, the module ships in SPI mode with BS1 and BS2 both set to 0. To use I2C, move the resistors to the I2C position, where BS1 and BS2 are both set to 1. First, include the I2C library using include wire.h. Then define the SDA and SCL pins. In the setup function, call wire.begin, passing in the actual wired GPIOs 1 and 2 to initialize the I2C bus. The loop function is the core of the scan. It uses a for loop to iterate over all possible 7-bit I2C addresses from 0x01 to 0x7f. Inside the loop, wire.begin transmission attempts to initiate communication as a master with the currently iterated address. Then, wire.end transmission ends this attempt and returns a status code. If it returns 0, it means success, indicating that there is a device at that address responding. Then, use serial.printf to print its address. Next, upload this code to the development board. Open the serial monitor, and you will see that every 5 seconds, the program scans and reports the results. The monitor prints I2C device found at address 0x3D, indicating that the address of our OLED module is 0x3D. If you disconnect the device, the program will report that no I2C devices were found. Now that we know the address, we can interact with the module. In actual development, we almost never need to manually write low-level I2C communication instructions because most sensor and module manufacturers or the community provide ready-made Arduino libraries. All we need to do is correctly configure the appropriate library to use the I2C pins we specified for the ESP32. Let's demonstrate by driving an OLED screen. This example requires the Adafruit SSD1327 library. First, search for and install it in the Arduino IDE Library Manager. The Library Manager may prompt you to install dependencies like Adafruit GFX. Choose Install All. After installing the library, go to File, Examples, Adafruit SSD 1327, and select the SSD 1327_test example. Let's look at this example code. This screen can be controlled using either I2C or SPI. This example uses I2C by default to control the display. The variables above are related to SPI control and can be ignored. In this example, find this line. It uses I2C by passing the wire object. To make the library use our custom pins, the method is very simple. Before calling the library's initialization function, call wire.begin to set the I2C pins. First, define the SDA and SCL pins at the top of the code, consistent with the actual wiring in the circuit. Then, in the setup function, call wire.begin with the specified pins. Then, compile and upload the code. After a moment, you will see the display start showing various test patterns. Finally, let's look at a more advanced example, allowing two ESP32 boards to communicate over the I2C bus. One acts as the master, the other as the slave. Components needed: two ESP32 boards, two breadboards, two 4.7 kiloohms resistors, a few jumper wires. Connect as shown. Note, the SDA of both boards are connected together and the SCL are connected together. G&D must also be connected. Pull-up resistors need to be connected only once on the bus. Although this example can run without external pull-up resistors, for signal stability, it is recommended to connect them. First example, master reads data from slave. In the master, the setup function initializes wire normally. The core of the loop function is wire.requestFrom. This line means request 5 bytes of data from the device with address 8. Then use wire.doThread to read the received data and print it. In the slave, during setup initialization, the first parameter of wire.begin is 8. This means it is no longer a master, but registers itself as a slave on the bus with address 8. Providing an I2C address initializes the device in slave mode. Omitting the address defaults to master mode. The most critical line is wire.onRequest. It registers a callback function. When the controller requests data from it, the request event function is automatically executed. Inside the request event function, we call wire.write to prepare the data and send it to the master. Upload each sketch to its respective board. Open the computer port connected to the master and view the serial monitor. You will see it continuously printing hello received from I2C. Now look at the other example. The master sends data to the slave. In the master code, we repeatedly call wire.begin transmission, wire.write, and wire.end transmission. The function of this combination is to send data to the device with address 8. Here we send a string x, is, and an ever-incrementing number x. In the slave, this time, we register the wire.onReceive callback. When it receives data from the master, the receive event function is triggered. Inside the receive event function, we use wire.available and wire.read to read all the data in the buffer and print it to the serial port. Upload the code again. This time, open the computer port connected to the slave and view its serial monitor. You will see the master's messages printed continuously. X is 0, X is 1, X is 2, and counting up. Press the reset button on the master, and X starts from 0 again. All right, that's all for this lesson. Let's quickly recap. We learned the core principles of I2C communication, including the SCL SDA signal lines, master-slave architecture, device addresses, and pull-up resistors. We practiced scanning for I2C device addresses and customizing I2C pins to drive an OLED display. We also implemented I2C master-slave communication between two ESP32 boards. In the next lesson, we will learn about another common communication protocol, SPI. Thanks for watching, and see you next time.